So, in our last class we have seen two types of finite automata, non-deterministic finite automata and deterministic finite automata, that is NFA and DFA. So, NFA is non-deterministic in the sense that at some states, so we have got a choice whether to make a transition on a particular input to one state or the other, or also there are epsilon transitions. So, without consuming any input, whether the machine should make a transition from one state to the next. Whereas, the deterministic finite automata did not have this type of non-determinism. So, here there everything is deterministic. So, from one state on a particular input input pattern or input symbol, it will go to one of the next state. So, if there are no transitions defined for a particular input symbol, then it is an error. So, the string gets rejected. But if we compare this NFA and DFA, apparently it seems that NFAs may be more powerful because it has got non-determinism in it. So, or somebody may say that okay, DFA is better because DFA there is no non-determinism. But theoretically it can be proved that this NFA and DFA, they are equally powerful as far as the set of languages that they can accept. So, this set of languages will be called regular languages. So, we will define regular languages later when we go to the grammar portion in the chapter on parser. But these regular languages are a class of language where it is a bit restrictive compared to many others, but this NFA and DFA both of them accept the same set of regular languages. So, any regular language which is accepted by a DFA, you can have a corresponding NFA, and whenever you have got an NFA, so you can get a corresponding DFA. So, there is power wise there is no difference. However, DFAs are easier to implement because there is no choice to consider. So, we can have we can do it very easily. So, we can have some sort of table driven algorithm by which we can make the transitions for the DFA. But there are other issues that we have are like this. Other issues that we have is say NFA versus DFA. For a given language, the NFA can be much simpler compared to a DFA. So, here is an example that we see. So, we have got the in the NFA. So, this is accepting the strings which are ending with 2 zeros. So, in this case it is ending with 2 zeros. So, it is 0 0 it is going to the end state or final state, otherwise it is remaining in the initial state. The same NFA or same regular expression. So, if you want to, so this regular expression corresponding to this is 0 or 1 star followed by 0 0. So, this regular expression, so if you want to realize by means of DFA, you will get a diagram like this. So, you see the number of states in both the finite automata are same, however, there are more number of transitions, and we will see an example where we will find that this DFA can be exponentially larger than NFA. So, we will next look into an example which will be doing that. So, consider a regular expression for this particular language. Suppose I have got it is written like this. So, it is the nth character or nth symbol from end must be A with alphabet set the alphabet set sigma equal to A B. Now, if we try to construct the corresponding finite automata, the NFA construction may be like this. So, this is the start state 0. So, as long as so you get A or B, you remain in this state. So, I said that the nth character must be A. So, if this is the nth character, so on A it makes a transition to state 1, then either on A or B it goes to state 2, then either on A or B it goes to state 2 state 3. So, this way it goes on. Okay. So, if it is maybe that the final state. So, this is our state n, this is our state n, and on getting A B it goes here. So, you see that here so this is a final state. So, this is a final state. So, this if the nth character is A, then only the strings are going to be accepted. But for the same thing, for the same regular expression, so if we try to draw the corresponding DFA, then the situation will be very different. So, let us take say n equal to 3. Okay, let us take n equal to 3, and for that we try to construct the corresponding DFA. So, if n is equal to 3, then the corresponding regular expression is given by A or B star followed by A, and then the next few characters may be AA, AB, next two characters can be BA or BB. So, this is the regular expression. In fact, this particular case where this is general, that is there the nth character from the end. So, you cannot have a regular expression for that. Okay. But when n becomes fixed, so like n equal to 3, then you can write down this regular expression. Now, for this regular expression, so if I try to draw the corresponding DFA, then it will be something like this. So, let us take a new page and then do it. So, my regular expression is A or B star, then A, then A or B, sorry. So, this is A or B star, then A, then you have got AA or AB or BA or BB. So, this is the regular expression. So, if you start at state 0, this is my state 0, as long as you get B, you remain in this state. So, if you get an A, so basically I am trying to capture this A sequence. So, you come to state 1, then if you get another A, come to state 2, if you get another A, come to state 3, which is a final state. So, this captures the sequence AAA. Now, if you get after after getting the first A, if you get a B, that is you have to define the transition on B. So, on transition on B, you can maybe from this state, if you get a transition on B, you come to a state 4, and from this state 4, there can be several situations, like if you get an A, then you see how did you come here is that if you get an A here, then you can go to this state, because then the third character from the end is really becoming an A, and if that is the end of the string, then this is valid. So, this is the thing. Similarly, from this state 1, if you get a B, you come to state number 5, and from state number 5, if you get an A, you come to state 6, and again state 6 is a final state, because the third character from the end is an A. So, to reach state 6, you have come via this path A B A. So, this A is the final, this is the third the third most character. So, this 6 is also a final state. Okay. Now, from this state 5, if you get a B, then also you come to a state 7, but this 7 is also a final state, because here also the last characters are B, B and A. So, that way it is correct. However, from state 7, if you get a B, so you go back to the first state, state 0, and from here also, from state 6 also, if you get a B, you go to state 0. Okay. Now, from state 7, if you get an A, then you have to come to state 1, because now A, B, A and all those sequences can be managed. So, on A you have to come here. Similarly, from here also on getting A, you have to come to state A, and from state 4, if you get a B, then it is like A, B, B. So, then that is also a final state 7. So, you see that what is happening is the diagram is becoming very complex. Number of states in this case is equal to 8 compared to the previous, like if you are doing it using NFA, then you will do it like this. So, at this state it is A or B, then on A you go here, and then so this is 0, 1, then on A or B you go there, A or B, so state 2, 3, and 3 being a final state. So, this was the NFA. So, getting the third most character as A, so it is going to a final state. So, here it was only a 4 state machine, here I have got a 8 state machine. So, that way number of states are increasing significantly. So, that can happen. Okay. So, in a more pathetic situation, so it may go to the number of states may become exponential in the case of a DFA. So, DFAs are better because if you are trying to develop a recognizer, then working with DFA is easier because everything is deterministic. So, the detection algorithm, there will be no non-determinism in it, but at the same time the size of the DFA may be very large. Okay. So, compared to the NFA. So, for our understanding, we should we will work with NFAs most of the time, and then do something so that NFA can be converted to DFA for the sake of implementation. So, this is exactly what is done by the lexical analysis tools, like given the regular expression. So, it first constructs the NFA, and from the NFA it converts it into a DFA. So, in the coming few slides, so we are going to see how this is going to happen. So, regular expression to finite automata, the avenue that is taken is like this, that is, we start with the lexical specification. From the lexical specification, which is an English language description, like the third most character from the end should be A, like that is the lexical specification. From there we write down the regular expressions. So, after the regular expressions have been written, so we convert these regular expressions to NFA, and then from this NFA we convert it into DFA. So, there is a conversion algorithm that we will see that can convert a non-deterministic finite automata to a deterministic finite automata. So, basically all the equivalent states of the non-deterministic finite automata, so they are clubbed together and they constitute one state in the DFA. And from regular expression to NFA, so this part, so there are some well defined rules which will convert, which will do this thing, regular expression to NFA. And once we have got the DFA, then we can have a table driven implementation of the DFA. So, which will be which will give us the recognizer for the language. So, next we will slowly go into the portion regular expression to NFA. Like say we will be using this particular notation. Suppose we have got a regular expression A. So, the corresponding NFA will symbolically represent it like this. So, this A is basically there are a number of states which there are transitions between them which constitute the NFA for A, for the regular expression A. But for our construction purpose, we will represent it in this fashion, that is as if, so there is a final state and there is an initial state, and this arrow means that this will go to the initial state of the NFA for A. So, this notation we will be using quite a few times in our discussion. Next, we consider individual symbols like say epsilon. So, if your regular expression A is equal to epsilon, then this A regular expression is converted into an NFA like this. So, this is the start state identified by arrow coming to it, then this is the final state identified by two concentric circles, and there is an edge from initial state to final state whose label is epsilon. So, this is the regular NFA corresponding to the regular expression epsilon. Similarly, for the regular expression A, the corresponding NFA is represented like this, that is from the initial state and a final state, and then edge between them is labeled by A. So, this way we will be doing the things for individual symbols that we have in the regular expression. Now, what about two regular expressions coming together, like A is a regular expression and B is a regular expression. Now, we have got a new regular expression which is A followed by B, like say your A may be the regular expression say AB star, and say B may be the regular expression A star. So, AB is the regular expression A, B star, A star. So, how to construct the corresponding NFA? With the situation in which we have already constructed the NFA for A and we have already constructed the NFA for B. So, the first part is the NFA for A, second part is the NFA for B. So, from the final state of A, we add an epsilon transition to the initial state of B, and this state no more remains a final state, because this is not the end of the regular expression. So, this way we do it. So, if there are multiple initial states in this then there will be multiple such epsilon transitions, or you can say, of course, normally we have only one initial state. So, the possibility is that there are many final states in A, and this is the initial state in B. So, we will have a edge coming from all of them, and all of them will be labeled epsilon. So, this way we do it. Okay. So, for AB, so one regular expression followed by another regular expression. So, we take the final states of the first regular expression, from there we add epsilon transitions to the start state of the next regular NFA for next regular expression. Next, we will see how to do the regular expression for A or B. So, again A and B are two regular expressions, and the new regular expression formed is the regular expression A or regular expression B. And as our assumption, so we have already constructed the NFA for regular expression A, which is this part. We have already constructed the NFA for regular expression B, which is this part. Now, for constructing the NFA for A or B, what we do? We introduce two new states, one initial state and one final state, and the initial state or the start state becomes the start state of the whole regular expression A or B. We add epsilon transitions to the initial states of A and B. So, like this. So, here we add epsilon transitions here, and add epsilon transitions to this the initial states, and from the final states of A and B, we add epsilon transitions to the final state of the newly created final state, the final state for the whole expression. So, this is how we do it for A or B. So, these are quite intuitive, because you can go either by this path or you can go by this path. But and in the first case, when it is A B, so you have to go through like this. So, A followed by B, from going from A to B, you do not consume any new symbols. Similarly, while taking a decision like whether we should go to A or B, we do not consume any input. Okay. So, that way this part is realizing the regular expressions A B and A or B. So, the more complex situation comes when we have got the regular expression A star. So, we already have the NFA for A. So, this is the NFA for A. Then we add two new states to the system. One is a start state, and one is a start state, and one is a final state, and we add epsilon transition. So, from the start state we add epsilon transition to the start state of A, and from the final state of A we add epsilon transition to the newly created start state, and also we add epsilon transition from the start state, newly created start state, to the newly created final states. And the final state of A, it is no more the final state. Okay. So, because the transitions have been added. So, you see, in this way if we do it, then the advantage that we get is, suppose there is zero occurrence of A, because it is A star. So, suppose we have got zero occurrence of A, then it will be going by this epsilon transition. If it is one occurrence of A, then it will go like this, with epsilon it will come to A, it will go like this, then through epsilon it will come back here, and then by epsilon it will come to the final state, one occurrence. If there are two occurrences of A, then it will go like this, then come back by epsilon like this, and then again go through A, one more cycle coming via this epsilon, then again come here, and then via this epsilon it will go to the final state. So, as many time you want, depending upon the number of times this A appears. So, you can just go on moving around this NFA, and finally, when you reach the end, so you can come by this epsilon to the final state. So, this way you see that we have got a few set of rules for constructing the NFA for individual types of regular expression, individual symbols, epsilon, then consecutive appearance of two regular expressions, or of two regular expression, and this one or zero or more occurrences of the regular expression. So, This way we can construct the NFA. Let us take an example. Suppose we have got this particular regular expression 1 or 0 star 1. Now, how do we do it? So, see, if you look into the individual components, then we have got a regular expression 1, regular expression 0 and regular expression 1. Now, how do you construct a regular expression for 1? So, it is like this. So, this is a final state, this is the start state and it is labeled with 1. Similarly, this 0 regular expression for 0, so you can construct it like this. On 0 it goes here. Now, once we have done that, the next part is to construct the regular expression for 1 or 0. Now, for 1 or 0, what we so we take the, so this is our A, okay. So, this is our A, this is our B, this is our B, and then we add two new states like B and G there, and from B we add epsilon transition to C and an epsilon transition to D, and from E and F we add epsilon transitions to G. So, that way, so now this whole thing, it represents the NFA corresponding to the regular expression 1 or 0. After that, I have to take a star over this. Now, for taking star over this, what we do? We add a new state H here. Now, from we add a new start state A here, and from the start state A we add an epsilon transition to the initial state of 1 or 0. Then from the final state of the NFA for 1 or 0, so we add a transition epsilon transition back to A, and also from A we add an epsilon transition to the state H, the final state H. So, that gives me, so at this point we have got the regular expression. So, till this much we have got the regular expression NFA for the regular expression 1 or 0 star. With that, we have to add the NFA curve for regular expression 1, and this is the regular, this is the portion of regular expression 1. So, from the final state of the first NFA, we add an epsilon transition to the initial state of the other NFA, so the NFA for 1. So, this is done and epsilon transition is added. So, that way this whole thing becomes the NFA corresponding to this regular expression. Of course, there is a lot of scope of optimization, because you see that there are epsilon transitions like from E to G and then again another epsilon transition to A. So, ideally I should be able to do it like this. So, this part, this state G can be eliminated and both of them from E and F I can take them back to A directly. So, this type of optimizations can be done, but going by the set of rules we get this particular NFA. Okay. Now, once this NFA is there, what can we do with this? So, next thing that we can do is, so we are at this point. So, we have we started with the lexical specification, from there the regular expression, from there we have got the NFA. The next thing to do is to convert this NFA to DFA, and once we are done with that, then we will have a table driven implementation of the DFA. Now, how to convert this NFA to DFA? So, that part we have to consider, see. Now, so the basic idea is that for NFA to DFA conversion, the idea is to simulate the NFA. So, we simulate the non-deterministic finite automata, and each state of the resulting DFA is equivalent to a non-empty subset of states for the NFA. So, you start with the NFA and start simulating for a particular input symbol A and see how far it is going for without consuming any more input. Like here, so if you see this one, if you see say this example, so you see if you start with say 0, so without, if you are starting at state A, then without consuming any more input, with just an input 0, you can come from A to B to D to F to G, and then it is not adding anything more, because now it is going to come back to A only. So, this A, B, D, F, G. So, all these can be simulated for the input symbol 0. So, to construct the start state, we considered a set of NFA states which are reachable through epsilon moves from the start state. So, in this particular case A is the start state. So, you take all the states which can be reached from A using epsilon transitions only. So, the set of states are A, B, C, D, H and this I. So, all of them can be reached by the epsilon transitions only from state A. So, all of them taken together, so that set will constitute the start state of the DFA. So, this is what is said that the start state of the DFA is equal to the set of NFA states reachable through epsilon moves from the NFA start state. Then from any state S, we add a transition to state S dash in the DFA on input A if and only if, so this condition is satisfied. S dash is the set of NFA states reachable from the states in S after seeing the input A, considering epsilon moves as well. So, what has happened is I have started with the start state. So, a number of NFA states, so they have given me the DFA state, DFA start state S. Now, from these states, so from these individual states on A, you see where can you go. So, maybe this state on A it takes here. So, this state on A takes here. So, others they do not have transitions on A. In that case, so these two plus all the states which can be reached from here via epsilon transitions. So, all those states that can be reached from these two states via epsilon transition. So, that will constitute the state S dash. So, in the DFA I will have a state S, I will have a state S dash and the transition will be labeled with A. So, this is how we will add transitions to the DFA.